Okay, yeah. So, welcome. As I said, the Space Universities Network, otherwise known as SUN, is co-chaired out of the University of Bristol, University of Manchester, and University College London, with two PhD students at the University of Bristol, myself and Thomas, who help support the day-to-day running of the organization. SUN was started to develop kind of the space teaching within the UK, to help produce skilled graduates and share best teaching practice whilst developing industrial relevant curricula and promoting, at the time it started, space science engineering. But as space in the UK has developed since then, it's also space law, space humanities, and on. Um, we have over 100 members across member universities across, so over 100 member academics across about 50 universities across the UK, all teaching various space things. And you'll note on the map that it does follow the population density centers as you would expect. Um, and yeah, we are quite happy to continue expanding our network, promoting space teaching in the UK and sharing best practice. And I guess as a part of that, we have this opportunity for several students to be funded to go to the UK Space Conference in Manchester in July to present their research. And then I guess that's a very quick whistle stop introduction to Space Universities Network. And I will stop sharing this one. And then, yeah, we will pass over to Leonani. The floor is yours.
Thank you very much. I'm just going to share my screen because I have got some slides. Here we go. And I think I've shared my sound as well, so that should mean the movie works, which is good. Yeah. I use this as my first slide. Obviously, I hope you know where you are. You're at the Student Space Research Symposium. If you haven't worked that out by now, I will assume that you probably haven't been listening. So, so hopefully you have worked out where you are and why you're here. So I'm just going to start by telling you a little bit about how I got into space. The first thing I will tell you is that it is not from childhood. Things that I wanted to be growing up did not include astronaut. I probably did at some point because I think everybody nerds out about space and dinosaurs at some point between the ages of 0 and 10. But the things that I really wanted to be were an Olympic gymnast. That was never going to happen. An equestrian. This one really baffles me because I've ridden horses about 4 times in my life, and I was obsessed with this idea for about 2 years when when I was a child. I wanted to be a writer, so there's a picture of a friend of mine who's a writer up in the right-hand corner. And I wanted to be a vet until I found out how squishy medicine is. And then I didn't want to be a vet anymore. And the one in the bottom left is a picture I think probably most people recognize as Marie Curie. That's the one that stuck. So that's the one that really got me going into the idea of I want to be a pioneer of scientific discovery. So when I was in high school, because as you can probably tell from my accent, I'm not from the UK. This is the equivalent of doing your A levels. And I put a picture of myself in my senior prom dress because I think senior prom is one of those really stereotypically quintessentially American things that, that illustrates kind of how different stuff is from in the US from the UK. But the other thing that's different is the academics. So in the US, you do subjects all the way right through to your senior year until you go to university. You can take advanced placements courses in subjects you want to major in at university. So in my junior year, before my final year, I took AP History and English because I liked both those things and I was pretty good at them. So I did those ones. And I was going to do calculus, physics, and chemistry in my senior year. But instead, I went to university because I got a place at university early. And I thought, well, I might as well just go and learn these things there. So I may or may not have been a mistake. It certainly was a very intense first year, but I got through it. And eventually I did graduate. I got a BSc in chemistry. Bachelor's degrees are 4 years long in the US. And some of that is because the first year is very general. It's still a liberal arts degree until you get to your second year and you start specializing. So I started off as a physics major. Very quickly worked out that I wasn't enjoying that, and it had absolutely nothing to do with academics. It was the fact that I was one of 2 women out of a course that had 53 people on it, and I didn't want to be there or stay there. And a lot of the professors, unfortunately, on my course didn't want me there either. So I swapped to chemistry, which was not much nicer. And throughout my degree, I took additional options in physics and maths, not enough to have a minor, which was very silly of me. But once I got to the point where I started looking at jobs, all of the graduate jobs looked really boring. So I asked my project supervisor, I was doing a project in physical chemistry on chemical kinetics, what I should do. And she suggested I should look at doing a PhD. And she gave me contact information for a bunch of supervisors. I got in touch with them. I paid a few visits, and I ended up getting a fellowship to be able to study at the University of California in San Diego. So San Diego, if you don't know, is in California. It's very beautiful, very, very beautiful. But I spent 5 years in a basement uh, with a big laser and a giant vacuum chamber, looking at energetics and dissociation dynamics of reactive organic intermediates, which probably doesn't sound very spacey to you, but actually, this is probably closer to rocket science, in my opinion, than what I do now, because these intermediates are important in combustion reactions and jet fuel. And we wanted to understand how these short-lived radicals interact with species that are already in the upper atmosphere. Ultimately, one of the things that this got me was a job at NASA when I finished. So after my PhD, I became a postdoctoral research fellow. It was a joint appointment between Caltech and the Jet Propulsion Lab. Still in the basement. So this time I was looking at the kinetics of reactions rather than the dynamics, but it was very similar work. And so I spent 2.5 years doing that. And because I was at the Jet Propulsion Lab, and actually this kind of work, this sort of experimental science, is a very small part of what JPL does. A very big part of it is mission operations and the development of robotic spacecraft. So I met a lot of people who did that while I was working there, and I thought, how can I get myself out of this basement and into something a bit more space related? So after I finished, I went looking for some more jobs, and I finally got a job. And this might surprise you. It wasn't actually building things. It was in doing post-launch support. So this is a picture of me in the mission operations room at the Jet Propulsion Lab, which actually happened after I finished my my postdoc. This was once I was working on the Cassini mission. So the first mission I ever worked on was actually called Cluster, and I've got my Cluster shirt on today because Clusters was in operation for over 22 years. And it is an Earth mission that studied the plasma environment. So the idea was to use space as a bit of a laboratory to study all these processes of interacting highly energetic particles in a completely collisionless environment. Very hard to simulate this on Earth. Space is the perfect laboratory for this kind of thing. And so it allowed, for the first time, because it's a multi-spacecraft mission, the measurement of processes that occur in the Earth's magnetosphere and their interaction with the solar wind, and actually getting data that was both in space and in time because of the fact that there are multiple spacecraft. So my role on this was as a calibration and archive engineer for the magnetometer data. So we've got these 4 spacecraft, 3 of which are still in orbit. One of them has re-entered. It re-entered last September in these really highly elliptical orbits with an orbital period of 51 to 57 hours. And these identical sets of instruments that give you full coverage of all of the aspects of all the different plasma processes. The other mission that I worked on when I first started was Cassini. So I don't know how many people have heard of Cassini, but it's still the only spacecraft ever to have orbited Saturn. The picture on the left shows it in the vacuum chamber being tested just before, this is flight testing, environmental testing just before launch. And you can see all the little people in the bunny suits working around the bottom of it, and just gives you some idea of how big it was, about as big as an upended bus. And the photo on the right shows one of my personal heroes. Her name is Julie Webster. She was the mission operations manager for the entire spacecraft for pretty much the entire time I was working on it. And she had an absolutely encyclopedic knowledge of everything about the spacecraft. So she was kind of my hero. Well, not kind of, she is. She is my hero. And yeah, so getting to work with people like that is a really amazing thing when you work in the industry. So Cassini operations, what is operations, I guess, is kind of what this slide is mostly about. So what you're looking at here on the slide is a picture of the final orbits of Cassini before it actually crashed into the planet and burned up. in the upper atmosphere. So when you're doing operations, what you're doing is spacecraft commanding. So you're doing maneuver design, you're doing flight rule checks, data retrieval, and you're resolving any anomalies on the spacecraft or within the subsystem that you work on. So I really enjoyed this. It was great fun. And, especially when you realize that you can describe what you're doing as driving the spacecraft, which is pretty cool. It's not just you, but, you're in a team of people who get to drive the spacecraft, which is brilliant. So for the people who, are in sort of STEM subjects, science and engineering, this is kind of, I wanted to show you what is commanding, what does that look like? So this is an example of sort of some entries in a spreadsheet that show the amount of time that we have to do our different maneuvers. So this is the instrument that I worked on, which is called the magnetometer, was the prime instrument. And what it's doing is allowing the spacecraft to roll. So the calibration rolls for the magnetometer are three-axis rolls. So 2-axis rolls, you can see in this video, you can see the spacecraft spinning around its long axis. Nobody minds this too much. We have to do it when we point the antenna at the ground anyway, to downlink and uplink data. But 3-axis rolls mean it's tumbling around the y-axis, the z-axis as well, so the long axis of the spacecraft. And pretty much every instrument, apart from the magnetometer and a couple of the plasma instruments, absolutely hates this, because what it means is that you don't know what you're pointing at. So cameras not taking pictures when you're doing these rolls. But designing the rolls was one of the most fun bits of my job, because actually it was quite difficult to work out how to make the rolls work without violating quite a lot of flight rules. So that was one of the most time-consuming things I had. These 9-hour rolls, working out how to design them so we got the information we needed, without causing the spacecraft to start tumbling uncontrollably. Okay, just a little video. I don't know if people have seen this before, but this is about the end of the Cassini mission. So I'm just going to let this play because I think it's quite cool, and it does actually make me quite emotional, even 9 years after the end of the mission.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. Bridge program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
To the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
So on the 15th of September, 2017, I was at the Jet Propulsion Lab when we got the final loss of signal was called, and it was quite an emotional moment. Quite a few people actually retired the next day. They'd been working on Cassini since it was originally conceived in the 1980s. So it's really quite remarkable how captivating these sort of endeavors can be. And it's one of the reasons why I've been in a career related to space for so long. So my next job in space was actually to design and build a space instrument, which I hadn't done previously. This was ongoing while we were still operating Cassini, but the really exciting bits started to happen after it finished. So you may have heard of the JUICE mission to Jupiter. It's one of the European Space Agency's large class missions. It's been launched. It's on its way to Jupiter, and I worked on it from pretty much the very beginning. And we built the lab that I was in, built the magnetometer for it. So we start with the lab model, which is breadboarded. Oh, sorry, my animation's gone out of sync. Sorry. Engineering, structural thermal, soldier qualification, and then flight model. And all of that takes about 8 or 9 years to go from the lab model to the flight model to delivery of the flight model. And then actually, I think they're almost finished with this now, but the flight spare gets built. The ideal thing is for the flight spare to get built before launch, but the flight spare has actually only recently been completed. So if JUICE had blown up on the launch pad, we would be looking at a little bit of a delay between trying to launch it again. So this is the trajectory that the JUICE mission is actually taking to Jupiter. For those of you who like a bit of orbital dynamics, so you can see it going around the inner solar system a couple of times. It makes a couple of flybys. It did a pretty unique flyby, actually. One of those passes around past the Earth. Actually went between the Earth and the Moon, which is a little bit unusual. Then out past Mars. And finally, after, I believe it's about 8.5 years, the spacecraft actually heads out and gets to Jupiter and undergoes orbit insertion around Jupiter. Okay, so my current job is kind of different from from any of those things. So I'm an associate professor of space engineering at the University of Birmingham. So I'm responsible for both teaching and research. And on the teaching side, a lot of what I focus on is space mission analysis and design and space systems engineering and design. And one of the sort of key problems that I think is concerning for everybody is the issue of space debris, as well as the highly congested populations of mega constellations of spacecraft in low Earth orbit. And additionally, some of the things that have recently gone wrong in the geobelt, which you can see in this illustration in this animation in red, in the geobelt, where we've actually had a couple of spacecraft break up and leave a trail of debris there. And that is really problematic because that stuff's there forever. For things in LEO, sometimes some stuff gets deorbited or deorbits naturally as their orbit decays over time through atmospheric drag. But quite a lot of stuff that we put in space is stuck there and never comes down again. And once the spacecraft is defunct, we have no control over it. So there's a very limited amount of stuff we can do to mitigate this. As you know, as I say, deorbiting through the atmosphere is one of them. Putting things into a graveyard orbit is another. But a graveyard orbit is still in orbit, so we still have quite a lot of stuff in space. So we need new technologies to make something happen about this. Bernice touched on this in her talk. And one of the things that I'm working on in my group is the monitoring of satellites, conditional monitoring of satellites. So being able to do this not just with optical techniques, so with your sort of traditional camera, but with very high frequency radar. And very high frequency radar, which would be difficult to use on the ground or from the ground because of atmospheric attenuation, suddenly becomes possible to use in space. And because you can build a very small antenna that operates at these very high frequencies, actually you save quite a lot in terms of space, size, weight, and power in making measurements like the ones that you're looking at here. So these are simulations. These are not real data. I do feel like I need to say that quite clearly. But what you can see is that when you go from 75 gigahertz, which is the image on the left, to 300 gigahertz, which is the image on the right, you suddenly start to see not just the edges and the corners of things, but quite a lot of detail on the surface. And what this should potentially allow us to do is enable things like repair and understanding exactly what has happened to spacecraft as they age. Because most of the information that we get back, especially from spacecraft in GEO, this is a spacecraft in GEO, is mostly electronic data. So actually having this kind of information, these kind of images would be incredibly powerful and enabling for in-orbit servicing and manufacturing. So that's the kind of stuff I work on and a little bit about how I got there. So now it's your turn. So one of the things that we want to do is to help get you into space, because I didn't start off in space and I have ended up in space. I've really enjoyed it. And it's, it's not an ending point either. It could potentially be another stepping stone for you, but certainly we'd like to see if we could get some more people to have space be part of their career trajectory. So the funding that's being provided gives you 2 days entry to the entire UK Space Conference. So that's Wednesday and Thursday, the 16th and 17th of July. It will cover your travel expenses to and from Manchester within the UK. I feel it's important to point out. 2 nights accommodation, so the Tuesday and Wednesday night. So make sure you don't miss anything. You can go for the entire thing if you want to. And your food costs for the duration of the conference, as well as a lovely networking dinner, so you can meet and network with the other students and hopefully with some of the SUN members as well who are attending as part of the opportunity. And that would be on the Tuesday evening. Right, what do you need to provide in order to access this funding? So the way that the form works is it's fairly standard stuff at the start: your contact details, name, university, email address, your year of study. So this should be either undergraduate, or you could currently be in your year in industry, which is usually an intercalated year during your degree, and postgraduate taught students are eligible for this funding. In terms of discipline, there's science and engineering. I mean, they're the obvious ones, but economics and business. Sorry, I put economics twice there. Very important. Policy and law and humanities. And as long as it's related to space, we actually don't mind which discipline you come from. So you'll have 3 options for the type of application that you can submit. And we suggest you don't submit multiple ones, just choose one. So you can submit a written application, a video application, or an audio application. This is somewhat unusual. I don't think many proposal forms that I've ever come across have offered these kinds of options. So I really encourage you to take advantage of it, especially if you are more comfortable recording something, whether that's video or audio, than you are with writing. I think it makes a big difference, and it makes it more accessible to people whose strengths lie in places other than essay writing about themselves in English. So each of those options has the same set of 5 required questions. The only thing that's different is how you answer. So the first question is why you're interested in space. And that's a maximum of 250 words or 90 seconds of audio and video. What you think you'll get out of this opportunity is the next question. And again, it's the same word count and the same time limit for video and audio. The next question is about highlighting barriers that you've faced and how you've overcome them. So this could be something, it could be something related to your what you plan to present to your, if it's a project, to, for example, to the project you plan, but it could also be anything else you've faced and overcome. We're not expecting that bit to be necessarily about a barrier you faced in relation to getting started in space. And then finally, how have you demonstrated a passion for space? And so we're back to this. This is related to space things. The last question is about an abstract. So the abstract, if it's a written abstract, you've got 500 words. And if it's a video or audio, you get 3 minutes. So it's a total, this is the full application, full length of the application. The total is either 1,500 words or 9 minutes of either video and audio, just to give you some sort of perspective on how much time you might need to put into preparing your application. Filling in the form probably won't take that much time if you prepare your answers for this in advance, because you just need to upload files or copy and paste text from one document to another. So recommend you approach it that way, where you take these questions, you sit and you think about them and you answer them, and then you get ready to fill in the form before you actually click on the link and open it up. So my top tips for your application are: develop a narrative for your motivation. So if you can, have a thread sort of running through it that links together the different parts of your application. This isn't easy, I acknowledge that, but it will make a difference to how well you feel your either your presentation or your writing will flow. And try and tell your story as clearly as possible. You know, don't try and sprinkle as many kind of what you think of as buzzwords potentially into it. You don't need that. We just want to understand why you're interested in space and why you're so eager to come and participate in the conference. And that, following on from that, show your enthusiasm. I think this is something where people feel like, particularly when doing video or audio, that they need to speak clearly and seriously. Clearly, I would agree with. I don't think you have to be serious. I think you need to be enthusiastic and energetic. And if that means occasionally you repeat things or you stumble over yourself or you even say, which I do a lot, it's fine. It is absolutely fine. What people will remember is your keenness. They won't necessarily remember that, you know, you said X number of times, unless they're being mean. So I would hope they're not, and we're not mean. So spend some time thinking about what your title is. It will be worth it, because once you have a good title that you feel invested in and confident about, it really does help to make the rest of it much, much easier to do, whether that's writing or recording. Then you should go to the form. Make sure you've done all this prep in advance before you open the form, because opening the form is kind of a formula for sitting there and getting stuck and staring at an empty box going, oh no, I don't know what to write in here. So I think it's better to go off and try and answer the questions yourself before you actually open up the form. And above all, don't forget to press submit. That's the thing that sometimes people do forget. So yes, please do make sure that you submit the form at the end of it. If you're uploading your files for the video and audio, unfortunately, that's in a separate page. It's a Google form rather than the Office form. So yeah, you will need to remember to do this. Because you won't be sitting on that page looking at the form that has the submit button on it. So that's the other reason why I've put that there. Is unfortunately got two separate pages for non-written submissions. And yeah, that's it. I hope to see you at the conference. Thanks very much. Happy if anybody has questions.
Thank you so much, Emily.